We generally think of topology as rubber sheet geometry. This means that we usually care about the closeness or relative distance between points in a topological space, but we don't always need a rigorous notion of absolute distance between points. However, topological spaces that are equipped or can be equipped with a structure that provides a notion of distance can be incredibly helpful. To explain this better, let's use an example in the real coordinate space with some balloons. Suppose these two balloons represent open sets A and B in R2. A is the set of points a distance less than R1 away from the point X using the standard Euclidean distance. Let's define B similarly as the set of points a distance less than R2 away from the point Y. The collection of all such sets, also known as open balls, forms a basis for a topology on the real coordinate space. As it turns out, the topology generated here is the same as the product topology on R2. But distance isn't only useful and applicable in the real coordinate space because we can actually generalize these ideas further. Metrics provide us with a rigorous notion of distance that is incredibly useful not just in real vector spaces and analysis when it comes to concepts like limits and convergence, but also in a lot of areas of topology. So let's now define what a metric is in the most rigorous terms possible. A metric D on a set X is a function from x cross x to the reals satisfying three properties. First, the function is always non-negative and only equals 0 when considering the distance from a point to itself. This follows the way we view distance in our daily lives. Second, the distance from x to y is the same as y to x. Third, also known as the triangle inequality, requires that going from x to y, then y to z, is equal or longer than going from x to z. We now introduce the definition of the metric topology. If D is a metric on X, then the collection of all epsilon balls for epsilon greater than 0 is a basis for a topology on X called the metric topology induced by D. Furthermore, if X is a topological space, then X is said to be metrizable if there exists a metric D that induces the topology on X. Two questions now arise. First, what unique properties do metric topologies possess? And second, how do we know a topological space is metrizable? The first question helps us understand why these structures are useful. The second question is important because knowing that a topological space is metrizable gives us access to all of the properties of metric topologies. So let's now consider an application. Let D and D prime be two metrics on the set X. Let tau and tau prime be the topologies they induce respectively. Then, tau prime is finer than tau if and only if, for each x in X and each epsilon greater than 0, there exists a delta greater than 0, such that the open ball centered at X of radius delta by the metric D prime is a subset of the open ball also centered at X of radius epsilon by the metric D. This gives us a way to compare two topologies induced by two different metrics over the same space. Now consider an example using this lemma. We'll choose our space to be the reals, D to be the standard Euclidean metric, and D prime to be the discrete metric. First note that every open ball of radius 1 or less under the discrete metric is a single point set because every two distinct points are a distance 1 away from each other. However, the topology of the reals induced by the standard Euclidean metric do not contain any one-point sets. Therefore, every open ball centered at X that consists of a singleton under the discrete metric must be a subset of any open ball centered at X under the Euclidean metric. Therefore, the topology induced by the discrete metric is finer than the one induced by the Euclidean metric. This makes sense considering that the discrete metric generates the discrete topology. Whether we're discussing rubber sheet geometry or exploring interesting applications of metrics in topology, just as balloons can soar to new heights, so can we using the power of metric topologies and the beauty of mathematics.